Okay, let's continue with more examples. Let's revisit the factorial function one more time. And this time we're going to do what's called tail recursion. Now, in the previous version, we talked about the factorial. And this is it's a recursive program, but the way this factorial works is that we go down the stack frames to the point where we get the base class, and that base class returns a number that comes back, gets popped off the stack, and that number comes off the stack to build a bigger and bigger number until you get to the point that the main program called the factorial, that bigger number gets returned, and the main program can use it. Tail recursions build the answer as it goes down the stack. So let's take a look at what this is. It's a different way of doing this. And you generally need more parameters to do this. So I'm going to designate this as factorial tail, and I'm going to pass it 5, say 5 or 4 factorial. Okay, and we're going to start off with the factorial having a value of 1 because it's 1 times 2 times 3 times 4 times 5. So what we're going to do is say, well, 5 is equal to 0? No. This is the interesting case. This is the recursive case. In order to calculate 4 factorial, I'm going to say, well, let's go one less iteration. But for this iteration, I'm going to take 5, multiply it by the 1. And so far, I keep saying 5. I'm going to take 4, multiply it by the 1. And so far, I've generated 4. Okay, so factorial of 4, 1 is equal to factorial of 3. 4 times 1 is 4. Okay, now, this time, 3 is the first parameter. 3 is the first parameter. Return value is 4. Okay, I do 1. I call that same method 1 less time, 2. But I take that 3, multiply it by the 4. So I'm going to generate factorial of 2 times 12. Okay, even that's too complicated. Because we're trying to get this number to be 0. And once we get a number of 0, that we've recursed as many times as necessary and this return value will have the answer. So factorial of 2, we generated a 12. Factorial, that's equal to factorial of 1. Remember, 2 minus 1 is 1. I take the 2, multiply by 12 to get 24. So we call factorial 1 comma 24, and even that's complicated. Because what we need to do is say one more time, factorial of 0, 1 times 24, okay, is 24. So once we get, see, the first parameter is 0, we're done. We return to 24. And what happens is, what makes this a tail recursion is that 24 just gets popped off the stack. 24 gets returned, 24 gets returned, 24 gets returned through each level here, to the point where we get the answer of 24. Okay? And so what we want to do, as far as the user is concerned, the user doesn't want to see. The problem is, in order to do this type of recursion, is that we have to start it off with a value, and we can't really let the user do that. All the user needs to know, all the user wants is to say factorial tail, and all they want to know is say, what's the factorial of 4? They don't want to know from Adam that we have to start the recursion with the value of 1. So factorial tail comes over here. All right, and so this is the helper function. Factorial tail starts the recursion with that second parameter of 1, and then see, we're assuming, I know this isn't the same class, but say these two methods were in different classes, the user wouldn't be able to see the helper function. They would be able to see the public function. Okay, and so that's the tail recursion. We'll do one more. Perfect numbers. Do you know what a perfect number is? Well, it turns out, you can look this up on Wikipedia, but a perfect number is a number that whose factors, whose perfect factor, whose factors all add up to be equal to the number. Okay, so I do know that the let's take a look at this. 28 is a perfect number. 28 is perfect. Why? Because the factors 1, 2, 4, 7, 14. Now don't include the 28, even though 28 goes into 28. Okay, don't include the 28. If you were to add up all these factors, not including the number itself, which is a factor of itself, 1, 2, 3 is 1, 2, and 4 is 7. 7 plus 7 is 14. 14 plus 14 is 28. If those factors add up to be the number itself, it's considered perfect. Now, I don't know why that's perfect. I'll leave it up to the mathematicians. I offer you an iterative solution to this. Okay, I start off with my factors, starting off with 1. Don't include the number I plus plus. If I divides into number evenly, then sum it up. And then once I have that sum, if you could say that this number is equal to that sum, that's going to return true. How do we do this recursively? There's the recursive solution. Remember, recursion doesn't use loops, so don't start putting loops in your recursive method. And in order to understand this function here, you can see the public method is this guy. I pass it to 28, and it comes back true or false. Okay, notice it's public. The helper function requires that I have a sum of factors method. Okay, now sum of factors does what it's supposed to do, but let's give it some interpretation. I'm going to tell you this. Sum of factors, I pass it two numbers. We need to give some interpretation of what comes back. If the sum of factors, say I pass it 28 and 5, okay, I'm going to interpret that 5 as saying, give me the sum of all the factors, starting with 5, ending with 28, but not including 28. Those would be 7 and 14. That would be 21. The sum of all the factors starting with 5, 6, 7, all the way up to 28, not including 28. If I pass it 6, 28 comma 6, give me all of the sum of factors of 28, starting from 6, still 7 and 14. 28 and 7, okay, 28 starting from 7. Sum of factors from 7 to 28 would be 7 and 14. Okay, still 21. Give me the sum of factors of 28 starting with 8. Well, the 7's gone. It's just going to be 14, and so on and so forth. That's the interpretation you put on these on this. You assume that if I pass it those values, then the number that comes back meets that interpretation. So, here's the deal. Base case. If I is bigger than or equal to the number, the sum of factors is 0. Remember, if I were to give it 28 comma 28, the sum of all the factors is 0 because we don't include 28. Anything bigger than 28 is not a factor, so you can't sum it. It's 0. Done. Now, here's another, well, I don't know if it's a base case, but here's another case. If this number, mod I, is equal to 0, you found yourself a factor. So I'm going to take that I and add it to the sum of factors, 28 comma 1 more. See, don't include the I, just add, this thing is going to return the sum of factors, not including the I. Now, if that's false, execution goes to line 89. There's no I plus or anything. In other words, if I were to give it 3, 3 is not a factor of 28, so you would bypass this and say, well, sum of factors of 28 comma 4. Give me back all those values from 4 onward. And what you do is don't worry about all the sub-micro operations that are performed. Just assume that, hey, if this thing returns correctly, with a number 1 more than I, then just add I, and that's the value of the sum of factors starting with I. It's really, when you think about it, it's a pretty elegant way of coding. And once you have that sum of factors, this returns the proper value, and here we just compare it to number, and that works out. Boolean true or false. So let's go ahead and say, well, what was it called again? I forgot. Is perfect. Copy. Copy the is perfect, and let's say is perfect 28, and let's call this a Boolean. Boolean B, because that's what comes back. Boolean B, and is 28 perfect? Let's see. Yes, it is. Is 29 perfect? False. Okay. And we're done with all the simple examples, I think. Yeah, we're done with all the simple examples. We'll see you in the next video where we deal with arrays in recursion. Take care. Bye.